Hello everybody! I hope everyone's having a wonderful day. We're going to be talking about more properties of big O. So the next one I'm going to be talking about is if I give you, say for example, two complexity functions, f and g. If I were to sum the result of two complexity functions, so I give you f and I give you g, and say if I wanted to take those two functions and add them together, what I can say is if I just take the larger or largest of the functions over the sum here, so f or g, if I put that in a max function, so the max function just simply is this. If whichever of the two of these functions is larger, I take the maximum of those functions, okay, for a given n. So if I have these two functions, if I have a sum like this, it'll be big O of the max between these two functions. So we're going to try proving this claim. So I'll give you a brief example of what one of these would look like in a moment. So let me try proving this here for you. So let's try proving this claim together. So what do? I usually tell you what I need to prove first, right? Now remember, here, do I have anything I can work with on just as a given? I just know that f and g are complexity functions. So no, I have to prove this directly involving f and g, but I can't make any assumptions about f and g other than that they're complexity functions. So anyway, so let's try proving this. So we find constants, c, which is a positive real number, and n0, which is of course a positive integer, such that for all n greater or equal to n0, what it has to be true. I have to take this here, such that f of n plus g of n is less than or equal to c times the max function given f of n and g of n. So the big thing I need you to really remember here is that the max here, this is actually, I'm talking about a max function. So it's taking the larger of the results here. So sometimes it might be that g is always going to be the maximum value. Sometimes it isn't. The point is that it's a maximum among those two. This is a very important fact that's going to come up in the proof. So you're going to see here this general idea. Okay. Would you agree with me that f is in fact going to be less than or equal to itself? Well, yeah, we've seen that when we tried proving that big O is reflexive, right? It could also be that g of n is in fact larger than f of n for a given value of n. So would you agree with me that if I looked at f of n, this is indeed less than or equal to the maximum of these two things, because the max function will select the larger of the two values. But we know it's at least f of n, right? And the same is true here, right? I know this is also true. This gives me an idea of what I can pick for c. Does anybody see it yet? Well, I'll give you a tip. I have two terms over there. Maybe I could try to match each one of those with a max function like this. But how many terms are there? At least on this side. Two, right? So what I'm going to do is I'm just going to pick c is equal to 2. Then we find, what do we find? We got to find n0, right? Once we find n0 and we do it in a very clear way, we're all done. n0 so that for all n greater or equal to n0, f of n is plus g of n is less than or equal to 2 times the max of among f of n and g of n. Well, now I'm going to invoke that thing I just mentioned a moment ago, that observation I had. Well, for all n greater or equal to 1, both of the following things are true. I'm just going to write down what I just said before. Both f of n is less than or equal to the max of f of n and g of n. And of course, g of n is less than or equal to the max of f of n and g of n. So all I'm going to do is I'm going to take these two inequalities. Do you see what I can do with these? I want you to remember back to something we did in one of our earlier examples, where what I did is I had like a collection of terms, and I want to show you that one side is at least as big as the other side, so that I can bound at least one of the sides, so I can say, hey, look, this side is at least, it can't be more than what's on the right-hand side. That's what I'm going to do right here. So I have two facts I can play with. F of n is less than or equal to a max function, and g of n is less than or equal to another max function. But do you see that the thing I'm trying to prove actually is a sum of f and g, right? So that just simply means that I'm just going to do what? I'm just going to add over both inequalities. So for every n greater or equal to 1. Now remember, one thing I do want you to take notice of is that every time I specify a domain for a statement, this is very important because I'm making observations based on a given domain. So the domain is simply me specifying for what values my claim is for. So this is for n is greater or equal to 1. You'll notice that that plays a very important role in the proof. So make sure you state your domain for whichever statement you're making. So it's very important. So for every n greater or equal to 1, what's true? Well, I'm going to sum over both of those inequalities. So f of n plus g of n is less than or equal. We know that this is less than or equal to this, right? So I'm just going to replace f of n with that. The max of f of n and g of n plus, okay, what can I replace g of n with on that inequality? It's right here, right? This max function. Max of f of n and g of n. My writing's sort of melting in the microwave. It's kind of fun that way. So what does that mean? Well, this is equal to 2 times the max of f of n and g of n. So what should I choose for n0? Well, I just yielded the inequality here, and it's true for all n is greater or equal to 1. So I'm going to choose n0 is equal to 1, right? Why? Because that's for which this is going to be true. If I pick n0 to be any bigger than that, that's okay. But as long as it's at least 1, which is the smallest possible value I can pick, we're all good. Now I'm just going to write my conclusion. Therefore, by the definition of big O, f plus g is big O of the max between f and g. And we're done. We're done. Very much. Excellent. Do you see what I just did here? I just used that idea I had much earlier on, that bucketing strategy, where what I do is I derive an inequality for each of these, then I sum over those two inequalities. So I have one right here and one right there. I add those two inequalities together, and that's how I get this statement right here. So that's a very important part of this proof. So just as an illustrative idea here, so imagine if g of n, so imagine if g was, say, for example, n to the k, and say f was just n. Based on what we know about polynomials, you know if I were to sum over n plus n to the k, you'd agree with me probably that this should be big O of n to the k, right? For some constant k. So this is a direct invocation of this property. So notice that I just get it for free because it's just part of the property. Notice that n to the k has to be bigger than or equal to n for all n greater or equal to 1. So that's where I get it from, where k, of course, is in fact 1 or larger. So that being said, that concludes this example here, and hopefully you found this kind of interesting. So when we come back, we're going to see some more properties of big O. So I say thank you very much, and have yourself a beautiful day.